Okay, so we want to integrate x times y, where r is the region that is bounded by these four curves. So in the first quadrant. So I'm going to try to sketch this now. This is the x-axis, this is the y-axis. I'm going to do, this is an example from Dr. Yaskin's book. And I'm going to try to stay consistent with the notation that he uses. So these two curves I'm going to graph in red. So we have 1 plus x squared looks something like this. 2 plus x squared looks something like this. And then the other ones I'm going to write in blue. So I'm going to put these two in blue. So 3 minus x squared looks like this. And then 4 minus x squared looks like this. And 4 minus x squared looks like this. Okay, so the region that we are interested in integrating over is this region right here. Okay, so now we notice a few things. No matter whether we do the x integral on the inside or the y integral on the inside, we're going to have to split it up into two, and we're going to have to find the intersection of all of these curves and stuff like that. And so the idea is that we just want to make this into an easier region to integrate over. This is not an impossible region to integrate over, but for various reasons, it's just better to get a different region. So now we need to figure out what we want a transformation to be. Let's look at the red curves first. So notice that this first curve says 1 is equal to y minus x squared, and the other one says 2 is equal to y minus x squared. Okay, so now I think it's helpful if I can explain what my goal is. So let me sketch the UV plane. This is the v-axis. This is the u-axis. I want the red lines to basically be these vertical lines here. So for example, I might want this red line to match up with the line 2 plus x squared, or the curve y equals 2 plus x squared, and maybe this red line can match up with the curve y equals 1 plus x squared. And then something similar I want to have happen with the blue lines. So if this is r, what I'm saying is I want this rectangle here to be t inverse of r. So now I just need to find a transformation that matches up the boundaries like I want it to. Okay, so how can I do that? Well, using these equations right here, I'm just going to say u is equal to y minus x squared. If u is equal to y minus x squared, then the equation y equals, or 1 is equal to y minus x squared, that equation is the same as u is equal to 1, if you plug in u is equal to y minus x squared. And then the equation 2 equals y minus x squared is the same as u is equal to 2. So if I come down here, this would be u is equal to 1, and this is u is equal to 2. And with the blue, I have something similar. So I've got 3 is equal to y plus x squared, and 4 is equal to y plus x squared. So I'm going to say that v is equal to y plus x squared. And so the curve y is equal to 3 minus x squared becomes the horizontal line v is equal to 3, and v is equal to 3. And then the line 4 equals y plus x squared, or y is equal to 4 minus x squared, is the line v is equal to 4. Okay, so u is equal to y minus x squared, and v is equal to y plus x squared. So let's look at the change of variables formula. So I have some function that I want to integrate on r. What does a change of variables formula say? Well, it says I can integrate it in the UV plane. I'm going to have v on the inside. V goes from 3 to 4. Yeah, that's right. And then u goes from 1 to 2. Actually, I'm going to use a neutral color with respect to the problem here. So v goes from 3 to 4. U goes from 1 to 2. Is that right? Yeah, 1 to 2. Okay, so now we need the function x times y is the function that we're integrating. Okay, but now notice we have something different here. So in this problem, we know that u is equal to y minus x squared. We know that v is equal to y plus x squared. That's different than the problems that we saw before. In the problems that we saw before, we had x as a function of u and v. So now we're going to have to do something a little bit different. We're going to have to solve these equations for x and y in terms of u and v. Okay. So there's a couple of ways to do this. This is a system of equations. So let me just write it stacked on top of each other. So this is v is equal to y plus x squared. Okay, so the first equation, so we want to write x and y in terms of u and v. So u and v are like the knowns. So if I look at the top equation, this tells me that u plus x squared is equal to y. So then y is equal to u plus x squared. V is equal to y plus x squared. So this is equal to u plus 2x squared. So what this tells me then is 2x squared is equal to v minus u, or x squared is equal to v minus u over 2. And then so we only care about positive x's in this problem because we're in the first quadrant. So x is equal to the square root of v minus u over 2. Okay, now y is equal to u plus x squared. So y is equal to u plus v minus u over 2. So this is going to be v over 2 plus u over 2, or just v plus u over 2. Okay, so now y is equal to v plus u over 2, x is equal to the square root of v minus u over 2. So I can make one computation here. X times y, sorry, this is getting like incredibly messy work because I'm having the problems run together. Okay, so x times y is v plus u over 2 times the square root of v minus u over 2. Okay, so that's what x times y is. So let me plug that into the integral here. So this is v plus u over 2 times the square root of v minus u over 2. Now we have to find the Jacobian. Okay, so now this is going to be fun, or maybe very not fun, because what we have is the following. We have this is y, this is x, and now we need to take the derivatives. Now the derivative in the y isn't so difficult, but it's just going to be aggravating trying to take the u and v derivatives of x. Because typically what we would need is we would need the partial derivative of x with respect to u, the partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v. Okay, but I'm going to tell you a little secret here. So this is equal to the following. This is equal to the partial derivative of u with respect to x, the partial derivative of u with respect to y, the partial derivative of v with respect to x, the partial derivative of v with respect to y. Okay, and you might be wondering why that is, or sorry, 1 over that. Okay, and so why is that? Well, if you've taken linear algebra, it's because the determinant of the inverse is just 1 over the determinant of the matrix. That's really what's happening here. And then there's some transposition things that you have to go through. Maybe if this had been a normal semester and we weren't doing this from home, I would have explained this more. But for now, just take my word for it. Okay, so let me remind you that u is equal to y minus x squared and v is equal to y plus x squared. And the partial derivative of u with respect to x is minus 2x. The partial derivative of u with respect to y is 1. The partial derivative of v with respect to x is 2x. And the partial derivative of v with respect to y is equal to 1. Okay, and so the determinant of this is minus 2x, so that's minus 4x. So this is 1 over minus 4x because of the minus 1 here. Okay, but remember x, where did x go? X is just equal to this. So this is equal to minus 1 over 4 times the square root of 2 over the square root of v minus u. And this is equal to minus 1 over 2 times the square root of 2 times 1 over the square root of v minus u. Okay, so now let me bring that up here, and we have to take absolute values of that. So now this is going to be equal to 1 over 2 square root of 2, 1 over the square root of v minus u dv du. Okay, so this simplifies a little bit. That 2 and that 2 make 4. This square root of 2 and that square root of 2 make 2, so we have 1/8. So this is equal to 1 over 8. U still goes from 1 to 2. V still goes from 3 to 4. Now let's look at what the integrand is. Well, also, the square root of v minus u cancels with that square root of v minus u. And so what we're left with is v plus u dv du. And now this is a function that I'm going to let you integrate on your own, because it is definitely a function that you can do on your own, or definitely an integral that you can do on your own. Okay, so there were two new things here. One was coming up with a transformation. One was coming up with what that should be and what u and v should be. And we did that practically by saying, well, we want to integrate over a rectangle like that. What can I do to make that happen? Okay, and the next new thing was to realize that when we did it that way, we were defining u and v in terms of x and y instead of x and y in terms of u and v. And then so to compute the Jacobian, we had to use this trick right here. Okay, and then from at that point, things were kind of tedious, but much less tedious than they might have been otherwise. Okay, so please watch this video again if that was confusing. Probably even if it wasn't confusing, I would suggest that you watch it again just because there's several new things and it went quickly.